السلام عليكم ورحمة الله يعطيكم العافية شباب وصبايا. رح نحل هلا examples على chapter 14 the internal flow. In this example we have the following cases: a horizontal pipe, an inclined pipe, as we can see, upward, inclined, downward. So uphill and downhill, as we mentioned in the previous lecture. So all these pipes are of the same diameter, and if the flow is flowing with the same average velocity, which is of 6 meters per second, diameter of 2 centimeters, the length of the pipe is 70 meters long, the pipe is circular pipe. So the flowing fluid is glycerine, which is at 40 Celsius degrees. So what's required here is to find we need to determine the velocity profile and the pressure difference across this 70 meters long section of the pipe. First of all, for the glycerine at 40 Celsius degrees, we need the properties, the density and the dynamic viscosity. We can get them from the tables, and we find that the density is 1252 kilogram per cubic meters, while the dynamic viscosity is 0.3073 kilogram per meter second. The velocity profile for the velocity profile in fully developed laminar flow in circular pipe is given through this equation. It's mentioned here that the flow velocity at the center line is 6 meters per second, and from the velocity profile of fully developed laminar flow, we know that the maximum occurs at the center line. So this represents the maximum. So the velocity profile is given according to this equation, since this is the maximum velocity. So again, it's not the 6 meters per second is the velocity at the center line, not the average velocity. The average velocity for such fully developed laminar flow is simply half the maximum velocity as shown here, which is 3 meters per second. That's the velocity that would be used in the calculation of the volumetric flow rate. Okay. The volumetric flow rate is simply the average velocity, which is half the maximum velocity, times the cross-sectional area, which is of a circular pipe. So we calculate it, we get the value. The Reynolds number equals to density times the average velocity times the diameter divided by the dynamic viscosity. We find that the Reynolds number equals to 488.9. It is less than the 2300, which is considered as the critical Reynolds number. So the flow is actually laminar, and the assumption we used to get the velocity profile, the average velocity, are all valid since we have laminar flow. So the friction factor, now we calculate the friction factor since this is a circular pipe, laminar flow. So it's according to this relation, 64 divided by Reynolds number. We find it equals to 0.1309, and it's unitless. The friction factor is unitless parameter. The major head losses is calculated since there are no components in the pipe. We don't see any fittings or components, so the losses is just only due to the major losses. So the losses head equals to F times L over D times the average velocity squared divided by 2G. And we find this losses head equals to 105.1 meter. Now we apply the energy balance along the section. As we can see, there is no turbine, no pump. The velocity would remain the same. The flow is laminar all the way, so the alphas are equal. So the pressure drop reduced to this equation, rho g times z2 minus z1 plus hl. For the horizontal pipe, the z2 minus z1 is 0. There's no change in elevation. That's for the case of horizontal pipe. So the pressure drop equals to 1291 kilopascal, which is at the same time, this is the pressure loss as well. This is the delta PL, since there is no elevation change. The pumping power to compensate this pressure drop equals to simply this pressure drop times the volume flow rate, that equals to 4.87. Now, in case we have the pipe inclined upward by 15 degrees, then delta Z now has a value, and it's added to the calculation of the pressure drop, and now it equals to 1,366 kilopascal. We can see it's more. The volumetric flow rate upward now equals to the pumping power. The pumping power per the pressure drop upward, and that represents the change in the volume flow rate. So that's 3.57, which is a decrease of 5.6% in flow rate. That's if we have it upward. Okay, now this example 14.2, we need to calculate the pressure drop and head loss in a pipe. Again, this is a pipe. We can skip this since we already did it here. We calculated the head loss and the pressure loss. So it's the same. This is just major losses similar to the previous example. So let's move to another example. Let's check this example. This is again a pipe. Here in the English units, the procedure would be the same no matter what are the unit system used. So this pipe is of 2 inches diameter. The volume flow rate is of 0.2 cubic feet per second. The flowing fluid is water. The flowing fluid is water. So the flowing fluid is water. The length of the pipe is 200 feet. We want to determine the pressure drop, the head loss, and the required pumping power for flow over this 200 feet long section of the pipe. So first, the average velocity is calculated as the volume flow rate divided by the cross-sectional area. That gives us this value, 9.17 feet per second. To calculate the Reynolds number, it is dimensionless parameter, so it's unitless as well. So it's the same no matter what's the unit system used. After plugging in the values for the row and the mu, which we got from the tables, we calculate the Reynolds number to be 126,400, which is greater than the 4,000, so the flow is turbulent. In general, for the calculations, whenever it's greater than the 2,300, we treat it as if it's turbulent flow. We calculate the relative roughness parameter. We get the roughness for the pipe material, which is, in this case, it's stainless steel. So we go to table 14.2, we get the value for the roughness. And now in feet, since we're dealing with English unit system, and we calculate the relative roughness and found it to be 4.2 times 10 to the power minus 5. The friction factor, according to the Kudebrook equation, using iterative scheme, we calculate the friction factor to be 0.0174, or we can simply go to the Moody chart and get the friction factor. Since we know the Reynolds number, we know the relative roughness, we can calculate the friction factor. We may check how to use the friction factor, how to use the Moody chart, since these relative roughness and Reynolds number are unitless, so we can still use the Moody chart. So remember, this is 4.2 times 10 to the power minus 5, while this is 126,400. So 126,000, that makes it like 1.3 times 10 to the power 5. 1.3 times 10 to the power 5. If we go to the Moody chart, as you remember, it's in the appendix. It's in the appendix as well. Let's check the appendix, just 1 second. If we go to the appendix, Moody chart, that's figure A27. Figure A27. So if we go now to figure A27. That's almost the last page, or the one before the last page. This is the Moody chart. This is the Moody chart. Let's rotate it so we can see it. Okay, here. So we said that the relative roughness equals to 4.2 times 10 to the power 5 approximately. We are somewhere, this is 1 times 10 to the power minus 5, or 1 times 10 to the power minus 4. And so we are somewhere here. Somewhere here. We are somewhere here. And we are in the 1.3 times 10 to the power 5. That's 10 to the power 5. That's 2 times 10 to the power 5. So we are somewhere in here. And together with the relative roughness as 4 times 10 to the power minus 4. So we are somewhere here. If we go upward together with the 1.3, so we are somewhere here. So take a horizontal line, and then we can read the friction factor is 0.017. 0.017. Very nice. So it's the same as the value. It's the same as the value we got from using the Colebrook equation. For you to know that actually the Moody chart is based on this Colebrook equation. So again, we can either use the Moody chart or the Colebrook equation. Now to calculate the pressure loss, the pressure drop equals to the pressure loss in this case, since we don't have any pump, turbine, no change in elevation. We showed that in the example 14.1. So the pressure drop in this case also equal to the pressure loss. No components, so the pressure loss is mainly due to the major losses, which is according to this equation. Calculated, we find the value. Now for the head loss, it's simply the pressure loss divided by the specific weight. So we calculated the pumping power is the volume flow. Pumping power to compensate this loss is the volume flow rate times the pressure loss. So we calculate it as shown here. Okay. Okay. This equation is to calculate. This example is to calculate the diameter of an air duct. It tells us here that there's a heated air at 1 atmospheric and 35 Celsius degrees. We need these properties, the conditions of the flowing fluid to get the properties. To be transported in a 150 meters long circular plastic duct at a rate of 0.35 cubic meters per second. If the head loss in the pipe is not to exceed 20 meters, so that's the HL, obviously it's major losses, no components in this pipe. Determine the minimum diameter of the duct. Minimum diameter of the duct. For the case when we don't have the diameter, first of all, let's get the properties for the air at the given conditions. For the given conditions, we get the properties, the density, the dynamic viscosity, the kinematic viscosity for the air. And in order to find the velocity, we cannot, since we don't have the diameter. Also, for the Reynolds number, we cannot, the friction factor, they all are function of the diameter, same as for the friction factor. So what do? We have a set of equations, 4 equations with 4 unknowns. Solving them with an equation solver give the following. Or what we can do is we can do Swamy-Jain formula that we showed you in the previous lecture, which is this formula. So simply we have this formula, since we have all these parameters provided, so we can calculate the diameter and find it to be 0.271. It's mentioned here that this is a smooth a smooth pipe, and that's why the roughness here is substituted to be as 0. Okay, example 14.5, to determine the flow rate. Same as the previous example, now the duct length is doubled while its diameter remains the same. If the total head loss is to remain constant, determine the drop in the flow rate through the duct. So this is the velocity, assuming the diameter is the same as the one here, to the 0.267. So assume diameter is given. So the velocity is function of the volume flow rate, same as the Reynolds number, the friction factor. So what we do is we do again solve these set of equations and get the values, or simply we can use the Swami and Jain formula to calculate the volume flow rate, and we find it equals to 0.24 cubic meters per second, which is exactly the same as the one by solving these set of equations. So for the exam purposes, we always do the Swami-Jain formula, the Swami-Jain formulas. Now let's check another example, other examples. Okay, example 14.6, it tells us that there's this a gradually expansion. So it's a component, there's no major losses, it's mainly minor losses. It tells us that the expansion occurs from 6 centimeters to 9 centimeters, and it occurs gradually, so it's not a sudden expansion. The flowing fluid is water, flowing at average velocity of 7 meters per second, and the pressure at section 1 is 150 kilopascal. We want to determine the head loss in the expansion section and the pressure in the larger diameter pipe. The head loss is mainly minor losses. So in order to calculate the minor losses for the expansion or the contraction, the minor losses is always according to the higher velocity. So from here, from the basic mass conservation principle, we would know that the velocity in the smaller section is greater than the velocity in the larger section, okay, according to the conservation of mass. So here, apply the conservation of mass, we find the velocity at section 2. To calculate the losses head is here mainly minor losses head because we don't have pipe length, so minor losses. KL times the larger velocity again, which is V1 squared divided by 2G. How to get the loss coefficient? So here we have 6 centimeters, 9 centimeters. It's mentioned that the included angle is theta 20 degrees. It's mentioned that the walls of the expansion section are angled 10 degrees from the axis. So 10 degrees from this axis here. So the full angle here is 20 degrees. If we go to the tables of the loss coefficient and check the gradually expansion, which is here. So for theta equals to 20 degrees, that's this case. And diameter ratio, we have 6 to 9 ratio. 6 over 9, that gives us what? 1/3. So we need to interpolate. So approximately it's between these two, it's 0.33. So we need to interpolate between the 0.3 and the 0.3 and the 0.25. So by interpolation, the value of the loss coefficient is found to be 0.133. Sorry, 6 divided by 9, that's the 0.66. That's the 0.67, approximately 0.67. So let's go back here. 0.67, it's between the 0.6 and 0.8. So we interpolate between 0.1 and 0.15. And the value is found to be 0.133. 0.133. Again, the 6 over 9, it's not 1 over 1/3, it's 2/3 actually. It's 2/3, that's the 0.6 0.67. Okay, so now we have the head loss. In order to find the pressure at section 2, we apply the energy equation between sections 1 and 2. We know the velocities. We know the elevation is the same. So Z1 and Z2 are the same. The alphas is the same. The alpha 1, alpha 2, we assume they are equal to 1. And so here it's assuming that this is turbulent flow, so it's assuming that the alpha is equal 1.06. If no information was available, simply assume the value of this kinetic energy correction factor to be 1. So plug in the values for V1, V2, the HL, no pump, no turbine, so they cancel. Z1, Z2 are equal, so they cancel. Eventually, we find the pressure at section 2 to be 168 kilopascal. 168 kilopascal. So there was pressure increase from 150 to 168 kilopascal through expansion, which is expected. Drop in velocity is accompanied by rise in pressure. Okay, let's check another example. Let's see this example here. In this example here, 14.8, water at 10 Celsius degrees flows from a large reservoir to a smaller one through a 5 centimeters diameter cast iron piping system. So the material is cast iron. Determine the elevation Z1 for a flow rate of 6 liters per second in the pipes. Flow of 6 liters per second in the pipe. We want to know the elevation here. So it's obviously it's an energy equation problem. So we have the length of the pipe, we have the flow rate of the water in the pipe, we have the elevation of the bottom reservoir. Here we have components such as this is gate valve fully open. Here this is an elbow, both two elbows which are standard elbow and flanged. Okay, we have here at the entrance, we have sharp-edged entrance. That's where the flow enters to the pipe. And here we have a sharp exit where the flow exits the pipe. Okay, so from the loss coefficient tables, we get the loss coefficient values for the entrance, the standard two standard elbows, and the exit, which these values easily you can check the tables for the loss coefficient very easily to find these values as we did in the previous example. So now here at the beginning, since it's water at 10 Celsius degrees, we go to the water tables. At 10 Celsius degrees, we get the properties, density, diameter, viscosity in order to calculate the Reynolds number and determine what flow type do we have, whether it's laminar or turbulent. Assuming that we may have turbulent flow, let's for now get the roughness for the piping materials. Cast iron, we go to table 14.2. For the cast iron, we get the roughness of the surface. That's equals to 2.6 times 10 to the power minus 4. Now we apply the energy equation between 0.1 and 2, which represent the surface of the water in the top and the bottom reservoirs respectively. Apply the energy equation. Obviously, the pressure at 0.1 and 0.2 are equal and equal to the atmospheric pressure, so they cancel. And the velocity also, since they are large reservoirs, so it's almost stationary at the surface, so velocities are zeros. So the equation reduces. There is no pump or turbine in between 0.1 and 0.2. As we can see, there are no pumps or turbines, so the HP and HT they are zeros. So the equation reduces to form Z1 equals to Z2 plus HL. So the energy equation reduces to this form. We have Z2. We need to calculate Z1. We don't have HL until now. The HL is the sum of the major and the minor losses. In this example, we have both. In the previous examples, we only had either minor or major losses. But in this example, as we can see, we have pipe of specific length. Besides, we have components. So we have minor losses due to the components, and we have major losses due to the friction in the pipes. Okay, the pipes is of constant diameter, which is 5 centimeters. So there is no summation. As we mentioned in the previous lecture, if there are different diameter pipes, then we will have summation and different values for the friction, the length, and diameters. While here, since it's this constant diameter, that means the velocity won't change through the pipe according to the conservation of mass principle for incompressible flow. And what else? So the major losses is the friction factor times L divided by D. We have the total length is, as we can see, the pipe length horizontally is 80 meters and vertically 9 meters. So the total length is 89 meters. Pay attention here to this length of the pipe vertically here. The diameter is 5 centimeters. We need to, of course, to convert it to meters in order to be consistent in the units. The summation of KL, we got the KLs from table 14.4. For the sharp edge, it's 0.5. Notice here that we have two elbows, so there are two KL for the elbows, plus the KL for the gate valve, which is fully open, that's 0.2, plus the exit and the entrance here. First of all, plus we still need to find the friction factor. In order to find the friction factor, we need to determine the Reynolds number. The velocity is simply the volume flow rate divided by the cross-section area. We find it's equal to 3.06 meters per second. Calculate the Reynolds number, we find it's 117,000. It's greater than the 2300 critical Reynolds number, so it's turbulent flow. The relative roughness is calculated to be 5.2 times 10 to the power minus 3. And now we have the Reynolds number, we have the relative roughness. We go to the Moody chart and get the friction factor, and it's found to be 0.0315, which is the same as if we get it from the Colebrook equation. So either the Colebrook or the Moody chart. The summation of KL, again, there's KL for the entrance, that's one component. Two elbows, so that's 2 times the KL for a single elbow, since they are identical elbows. KL for the gate valve fully open condition, plus KL for the exit flow. And now we can calculate the head loss. It's found to be 27.9 meters. And plug it back into the energy equation here to solve for Z1, since Z2 is given as 4 meters. So solve for Z1, we find that Z1 equals to 31.9 meters. Okay, so that's all for the examples of chapter 4. يعطيكم العافية وبتمنى الكل يكون بخير وصحة وسلام يا رب. السلام عليكم ورحمة الله.